video here to talk about what proof by induction actually is, what it's useful for, why you would need it, how we use it in mathematics. We're not actually going to do proof by induction. We're just going to talk about what it is, because it's a very, very abstract concept, I suppose, but hopefully we can explain it easily. Now, as a kid, you might have had like a calculator, probably not this one, but a calculator, and you probably said 1 plus 2 plus 3 plus 4 plus 5. That's a fun game that grade 1s and 2s like to play. It looks like this. Alright, and you go on forever and ever and ever until you get bored or the bell goes or something like that. Now, the answer to each of these, so 1 plus 2, 1 plus 2 plus 3, 1 plus 2 plus 3 plus 4 is, 1 plus 2 is 3, 1 plus 2 plus 3 is 6, 1 plus 2 plus 3 plus 4 is 10, and so on and so forth. Now, as a kid, you might be mucking around with this and you might look at these numbers and start to see a pattern. And if you're a very, very bright kid, you might come up with an algebraic formula to tell you what, let's say if I did this 20 more times, what the 28th term might be. And your algebraic formula might look like this. N on 2 bracket n plus 1. And that's going to tell you the sum of the nth term of this particular sequence. So I can test it if I want by saying, okay, it's worked so far, I wonder if it'll work for 9. So I put 9 into my formula, 9 on 2 bracket 9 plus 1 equals, maths, equals 45. And then I do it manually and I find out that, yep, it equals 45. And then I start to celebrate and I say, yes, my formula works, obviously it can't go wrong. Now, that's fine for a 7-year-old or an 8-year-old, but mathematically it doesn't hold water. You've got to prove without a doubt that this will work forever until the end of time. It doesn't matter how many test cases, this is like a test case, it doesn't matter how many test cases you do. You haven't proved it until you've proved that it works for every single number from now until the end of time. It could be that this would keep working until we get to the number 1,256,000 and then it breaks down. We can't use test cases. We need a more rigorous proof. Here's the concept behind the proof by induction. Alright, the analogy most maths teachers use, and I'm no exception, is the dominoes analogy. So you've got your dominoes here, and your dominoes represent each term. So the first term here, the second term, the third term, the fourth term, and so on and so forth. So, the proof by induction is a 3-step process. Step 1, you assume that it works for k. Just for a random domino. Now, I'm not saying choose domino 6, I'm saying let a domino be k and assume it works. Assume this formula works. So that's step 1. Step 2 is prove that it works for k plus 1. Now, if you assume it works for k, and then you prove that it would work for something 1 more than k, that means that if we assumed that was k, then it works for this. If we assumed this was k, then it works for this. If we assumed this was k, then it works for this. So this was step 1. Assume that it works. We don't know it works yet, but just assume that it does. 2, prove that if it works for k, it also works for k plus 1. Once we've got these, we just need to go to the end of the row and knock over the first domino. So then 3, show it works for domino 1. Now, domino 1 is usually k is equal to 1, but not always. I'll show you some instances where that's not true. Now, if you show it works for 1, and 1 is k, then it works for k plus 1. And this domino knocks over this domino, and this domino knocks over this domino, and this row of dominoes goes on for infinity, and bam, we've proved that our formula that our 7-year-old student figured out is true beyond a shadow of a doubt. That is proof by induction. The algebra gets really ugly from here. Let's see how to do it.